All right. The problem is Koko eating bananas. So you're given a list of numbers. Each number represents a pile of bananas. You have 3 bananas, 6 bananas, 7 bananas, 11 bananas. You want to find the banana eating rate that allows all the piles to be eaten by the time um, the what do they call them? The guards return. The guards return in H hours. So let's say, for example, here we're eating um, what is it? Bananas per hour. Let's say we're eating 1 banana per hour. So the first pile would take us 3 hours. Let's take us 6 hours. At that point, we have 9 hours on the first 2 piles. That's greater than this. The guards will return before we ate all the bananas. So that won't work. So you want to find the number that allows Koko to eat all the bananas, but you want it to be as small as possible. Obviously, you could say 100. Maybe eat this in 1 hour, this in 1 hour, this in 1 hour, this in 1 hour. That'd be 4 hours. That's obviously less than or equal to 8, but that's 100. You could also do 50, and that'd be a more ideal K because it's smaller. So you want to do that. Now, a brute force solution here is essentially just going from 1 to the maximum K value, which the max K value you'd really want to consider is the maximum value in piles. Like, think about it. If you ate 20 bananas per hour, why would you want to do 20? Why not? It's like the 150 example I just had. Why would you do 20 if you could do 15? Why do 15 if you could do 12? Why do 12 if you could do 11? Now, if you go below 11, um, let's say you do 10, that would mean oh, that was a good one. If you did a 10, that would take you 2 hours to eat this pile. So obviously 11 would still be um, not the optimal answer, but it'd be the max you would want to consider. Because in case you need to do it where every pile is at most 1 hour, like let's say H was 8, and this would need to be 11, right? If you did anything more than 11, it would take 5 hours. What did I just say? Did I say H was 4? That's what I meant. I don't know if that's what I said. So with that being said, the max K is essentially the max value in piles, right? So we'd say for each K value in the range from 1 to the max of piles, that'd be plus 1 because for loops obviously are exclusive at the end. We'd say for each K value, let's total up how long it would take us to eat all the piles. So we'd say for each pile, piles, we'd say total plus equals. And to get this, let's say we're eating 2 bananas per hour. To eat 6 bananas, it would obviously take 3 hours, right? So it's P divided by K. Now let's say you're doing 7 though, at 2 an hour. 7 divided by 2 is 3.5. So how long would it take us? It would take us 3 hours or 4 hours. We need to either round up or round down. Obviously, we need to round up because if it takes us 3.5 hours to eat this, we wouldn't be able to complete it in 3 hours. So we just need to do the ceiling of this value. And then I believe what we do, so we have the total. If the total is less than or equal to H, we can just return K, right? And the reason we're doing that is because when we're going up through the the different K values, these are the K values. And we know this problem goes before because that's the answer. The total of 1 would be, the sum of all the numbers. So it'd be 10, 16, like 27. Sum of 2 would be, I don't even know. I think it's like 15 maybe. This one, I believe, what is it, 8? I don't even know. It doesn't really matter what the numbers are. Just the point is they get smaller as the K goes up, right? If you're eating 4 bananas per hour, it's going to take you less time to eat a pile, any given pile. Well, I guess a pile that's greater than 4, right? That's the reason we're doing this. As pretty much what we're saying is as soon as we find a K value where this number is less than 8, we're done. We don't need to keep going because again, we want to minimize K. So that makes sense, right? As K is increasing, this number is getting smaller. So as soon as we reach the threshold of less than or equal to H, we're done. We found K. We don't need to keep checking. So this is a brute force solution, and this works. The problem is, this works like theoretically. The problem is it's too slow. We'll get a time limit exceeded after a little bit. So, assuming I didn't make any errors. So what we want to do instead is the binary search approach. Right? It makes it just slightly more efficient. Right? So what we're doing in binary search, like we have to take into consideration both the k, which remember goes up as we're going through it, and then the total, which is reverse. It gets smaller as we keep going. But what we'll kind of use as, I guess, the values for the binary search for the left and right is going to be the k value. So we'll start it at 1. Remember, the max k is the max value of piles. And we'll do the classic binary search thing, as long as left is less than or equal to right. So k, normally in binary search, is called center. We'll just call it k because it's a little more clear. So k is the center value. What we'll do is we'll keep track of our total. So we'll go through, just like we did down here, right? P piles, we'll add the amount of hours it will take to eat a given pile based on the current k value. And then we'll use the total as kind of the key, right? The total is, we're checking, I guess not the key, we're checking if the total we found is how it compares to h. So if total is greater than h, we obviously have not found the k that we want. So we'll reset the left to k plus 1. So on binary search. And the reason we're doing this, if total is greater than h, let me write that. I think I have it written down here. Yeah. Let's say we're searching for, h equals 6. And here's our k value that we're testing. Remember, they increase as we go. And the total values, which we kind of written poorly, these, go this way essentially, right? They get smaller as they go. So what we're doing is we're like checking this. We're saying, okay, what's our total value? Our total value is 30. Okay, let's just say our h we want is, I don't know, let's just say it's like 10. Okay, our total value is less than 10, right? And what did our code say? If total is greater than h, well, we need to write the rest of it. Else total is less than h, which means this is at least a possible answer. It might not be the best answer, but it's a possible answer. So what we'll do is we'll do the opposite in the binary search. We'll do right equals k minus 1, right equals center minus 1, essentially is what that is. All right, so in this case, total is less than or equal to this. Right, this is total, this is h. So we'll say right is k minus 1. Of course, in this case, we were here. So we'd move right over here, k minus 1. And now the center would be, here, which in this case we do here because we're flooring it, or integer division. So now we do it again, okay. See, the key here is we actually need to keep track because of this problem, right, we just ran into, right? Because we just ran into the problem where we were here, and now we moved right over here. So now we're pretty much ignoring the rest of this. We are always going to be working with this subarray. And as you can see, these values will always be, the total values will always be greater than h, which means there is no possible solution on this part of the array, which means we need to have saved the best answer we could have gotten from this, the previous steps, which we didn't do every step, and these values aren't the best to show this, but so we need to essentially have a starting value, that we want to use just in case we don't find anything good. So remember again, max k, we said, was the max of all the piles, right? So in this case, it'd be 30. So we'd keep track of that. And when you do the process, each time you're about to shift the right, which means we're making total larger, before we do that, we need to say, okay, hey, we're about to move to a section of the array that has larger totals. This could potentially lead to us finding no value that is less than or equal to h, just because our total values are getting larger. If that's the case, let's stop. Let's save k as max k. within that loop. Because remember, if we're moving right at all, right here, we already know total is less than or equal to h, and what this means in English is the current k value is a possible answer. It might not be the minimum answer, but it's a possible answer. So each time we're about to move right, we want to say save the k real quick, just in case this is the best answer we run into. Right? Now let's say we're looking for, I don't know, let's say we're looking like 52. So if we're here, we have our max k as 30. That's the best answer we have so far. We use that just kind of heuristically based on the max pile. So looking at center, we'd say, okay, is this less than or equal to this? It is. Okay, let's move left here. Right? Now our center is here. Let's say, is that less than or equal to it? Yes, it is. Okay, let's save this real quick. This is actually a good example showing what I was trying to show. Now that I think about it. Okay, we got a better example. Restart this here. Let's say h is, I think, 20. Let's just change this to be like 28. Okay, so one more time. Left, right, center. So, is this value less than or equal to it? Yes, it is. Okay, which means we're going to be changing right. Remember, we're going to be changing right. We're going to be shifting right to the left center. So before we do that, we'll say, hey, let's save this real quick just in case we don't find anything better. Okay, then we'll move our right over here. You see, now we've saved the best value. That doesn't even make sense. Oh, I'm stupid. 28 is not less than or equal to 20. Brain dead. Okay, it's not less than or equal to, it's greater than, which means we shift left to the right. So we move left here. We calculate center to be here. And now we're saying, okay, is this less than or equal to what we're looking for? Yes, it is. Let's save that. Because again, now what I was saying, if it's less than or equal to, we're shifting right. Which means we need to save the k just in case. Because you see here, move right here, and now we're done actually in this case. Okay, you know what? Yeah. I should have came up with better examples beforehand. Point is, whenever you're shifting to the left, whenever you found an answer, because you're shifting right to the left, you're going into larger total values territory, which means you might not be able to find another answer that actually works, that actually is less than or equal to h. Which means you need to save the current k just in case it's the best you can get. So the current k, at the end, we'll just return best k. Because the thing is, this process, I had one iteration of the code that didn't work, and what I would do, I didn't have this. I would just return k at the end. Because this code, in normally binary search, when you find a value you're looking for, right, you have a clause up here that says, you know, if total equals h, right? If we found the thing we're looking for, we'll return true or the index or whatever. In this case, we're not doing that. We don't want to take the first valid answer that works. We want to find the minimum one. So we need to keep going until we've pretty much zeroed in on a single value. And because we might end up zeroing in on a value that's greater than h, that's why we save this. There you go.